The history of navigation is the history of seamanship, the art of directing vessels upon the open sea through the establishment of its position and course by means of traditional practice, geometry, astronomy, or special instruments. A few people have excelled as seafarers, prominent among them the Austronesians, their descendants the Malays, Micronesians, and Polynesians, the Harappans, the Phoenicians, the ancient Greeks, the Romans, the Arabs, the ancient Tamils, the Norse, the ancient Bengalis, the Chinese, the Venetians, the Genoese, the Hanseatic Germans, the Portuguese, the Spanish, the English, the French, the Dutch and the Danes. Antiquity. Mediterranean. Sailors navigating in the Mediterranean made use of several techniques to determine the location, including staying in sight of land and understanding of the winds and their tendencies. Minoans of Crete are an example of an early Western civilization that used celestial navigation. Their palaces and mountaintop sanctuaries exhibit architectural features that align with the rising sun on the equinoxes, as well as the rising and setting of particular stars. The Minoans made sea voyages to the island of Thera and to Egypt. Both of these trips would have taken more than a day's sail for the Minoans and would have left them traveling by night across open water. Here the sailors would use the locations of particular stars, especially those of the constellation Ursa Major, to orient the ship in the correct direction. Written records of navigation using stars, or celestial navigation, go back to Homer's Odyssey, where Calypso tells Odysseus to keep the bear, Ursa Major, on his left-hand side and at the same time to observe the position of the Pleiades, the late-setting Bootes and the Orion as he sailed eastward from her island Ogygia, traversing the ocean. The Greek poet Aratus wrote in his Phenomena in the 3rd century BC detailed positions of the constellations as written by Eudoxos. The positions described do not match the locations of the stars during Aratus's or Eudoxos' time for the Greek mainland, but some argue that they match the sky from Crete during the Bronze Age. This change in the position of the stars is due to the wobble of the Earth on its axis, which affects primarily the pole stars. Around 1000 BC, the constellation Draco would have been closer to the North Pole than Polaris. The pole stars were used to navigate because they did not disappear below the horizon and could be seen consistently throughout the night. By the 3rd century BC, the Greeks had begun to use the Little Bear, Ursa Minor, to navigate. In the mid-1st century AD, Lucan writes of Pompey, who questions a sailor about the use of stars in navigation. The sailor replies with his description of the use of circumpolar stars to navigate by. To navigate along a degree of latitude, a sailor would have needed to find a circumpolar star above that degree in the sky. For example, Apollonius would have used Beta Draconis to navigate as he traveled west from the mouth of the Alpheus River to Syracuse. The voyage of the Greek navigator Pytheas of Massalia is a particularly notable example of a very long, early voyage. A competent astronomer and geographer, Pytheas ventured from Greece through the Strait of Gibraltar to Western Europe and the British Isles. Pytheas is the first known person to describe the midnight sun, polar ice, Germanic tribes and possibly Stonehenge. Pytheas also introduced the idea of distant Thule to the geographic imagination, and his account is the earliest to state that the moon is the cause of the tides. Nikos's celebrated voyage from India to USA after Alexander's expedition in India is preserved in Arrian's account. The Indica. Greek navigator Eudoxus of Cyzicus explored the Arabian Sea for Ptolemy VIII, king of the Hellenistic Ptolemaic dynasty in Egypt. According to Posidonius, later reported in Strabo's geography,
The monsoon wind system of the Indian Ocean was first sailed by Eudoxus of Cyzicus in 118 or 116 BC. Nautical charts and textual descriptions known as sailing directions have been in use in one form or another since the 6th century BC. Nautical charts using stereographic and orthographic projections date back to the 2nd century BC. In 1900, the Antikythera mechanism was recovered from Antikythera rec. This mechanism was built around 1st century BC. Phoenicia and Carthage equals. The Phoenicians and their successors, the Carthaginians, were particularly adept sailors and learned to voyage further and further away from the coast in order to reach destinations faster. One tool that helped them was the sounding weight. This tool was bell-shaped, made from stone or lead, with taller inside attached to a very long rope. When out to sea, sailors could lower the sounding weight in order to determine how deep the waters were, and therefore estimate how far they were from land. Also, the taller picked up sediments from the bottom which expert sailors could examine to determine exactly where they were. The Carthaginian Hanno the Navigator is known to have sailed through the Strait of Gibraltar c. 500 BC and explored the Atlantic coast of Africa. There is general consensus that the expedition reached at least as far as Senegal. There is a lack of agreement whether the furthest limit of Hanno's explorations was Mount Cameroon, or Guinea's 890-metre (2,910-foot) Mount Kakolima, Asia. In the South China Sea and Indian Ocean, a navigator could take advantage of the fairly constant monsoon winds to judge direction. This made long one-way voyages possible twice a year. Medieval age of navigation. The Arab Empire significantly contributed to navigation, and had trade networks extending from the Atlantic Ocean and Mediterranean Sea in the west to the Indian Ocean and China Sea in the east. Apart from the Nile, Tigris, and Euphrates, navigable rivers in the Islamic regions were uncommon, so transport by sea was very important. Islamic geography and navigational sciences made use of a magnetic compass and a rudimentary instrument known as a kamal, used for celestial navigation and for measuring the altitudes and latitudes of the stars. The kamal itself was simple to construct. It was a rectangular piece of either bone or wood which had a string with 9 consecutive knots attached to it. Another instrument available, developed by the Arabs as well, was the quadrant, also a celestial navigation device. It was originally developed for astronomy and later transitioned to navigation. When combined with detailed maps of the period, sailors were able to sail across oceans rather than skirt along the coast. Muslim sailors were also responsible for introducing the lateen sails and large 3-masted merchant vessels to the Mediterranean. The origins of the caravel ship, developed and used for long-distance travel by the Portuguese, and later by the rest of Iberians, since the 15th century, also date back to the Carib used by Andalusian explorers by the 13th century. The sea lanes between India and neighboring lands were the usual form of trade for many centuries, and are responsible for the widespread influence of Indian culture to the societies of Southeast Asia. Powerful navies included those of the Maurya, Satavahana, Chola, Vijayanagara, Kalinga, Maratha and Mughal Empire. In China between 1040 and 1117, the magnetic compass was being developed and applied to navigation. This let masters continue sailing a course when the weather limited visibility of the sky. The true mariner's compass using a pivoting needle in a dry box was invented in Europe no later than 1300. Nautical charts called portolan charts began to appear in Italy at the end of the 13th century. However, their use did not seem to spread quickly. There are no reports of the use of a nautical chart on an English vessel until 1489.
Vikings used polarization and the sunstone to allow navigation of their ships by locating the sun, even in a completely overcast sky. This special mineral was talked about in several 13th–14th century written sources in Iceland. Age of exploration. The commercial activities of Portugal in the early 15th century marked an epoch of distinct progress in practical navigation for Europeans. These exploration and trade expeditions sent out by Infante Henrique, later called Henry the Navigator, led first to the discovery of Porto Santo Island, near Madeira, in 1418, rediscovery of the Azores in 1427, the discovery of the Cape Verde Islands in 1447 and Sierra Leone in 1462. Combined with the empirical observations gathered in oceanic seafaring, mapping winds and currents, Portuguese explorers took the lead in the long-distance oceanic navigation, opening later, at the beginning of the 16th century, a network of ocean routes covering the Atlantic, the Indian and the Western Pacific Oceans, from the North Atlantic and South America, to Japan and Southeast Asia. The Portuguese discovered the two large volta do mar, meaning literally turn of the sea but also return from the sea, currents and trade winds of North and of South Atlantic Ocean, approximately in the first half and in the late 15th century respectively, that paved the way to reach the New World and return to Europe, as well as to circumnavigate Africa in Western Open Sea, in future voyages of discovery, avoiding contrary winds and currents. King John II of Portugal continued this effort, forming a committee on navigation. This group computed tables of the sun's declination and improved the mariner's astrolabe, believing it a good replacement for the cross-staff. These resources improved the ability of a navigator at sea to judge his latitude. Castilian Jew Abraham Zakat, the author of an exceptional treatise on astronomy, astrology and Hebrew, with the title Hajibah Hagadol, fled to Portugal in 1492. He published in the printing press of Leiria in 1496 the book Bio Lujo, or in Latin Almanac Perpetuum, which was soon translated into Latin and Spanish. In this book were the astronomical tables, ephemerides, for the years 1497 to 1500, which may have been instrumental, together with the new astrolabe, made of metal and not wood as before, created and perfected at the beginning of the Portuguese discoveries, to Vasco da Gama and Pedro Álvares Cabral in the voyages to India around the open Atlantic Ocean, including the southwest Atlantic, and in the Indian Ocean. Nevertheless, the Portuguese had to hire local pilots in the Indian Ocean for several decades to guide their ships. In the 15th and 16th centuries, the Crown of Castile and then the unified Crown of Spain was also in the vanguard of European global exploration and colonial expansion. The Spanish Crown opened trade routes across the oceans, especially the transatlantic expeditions of Christopher Columbus on behalf of Castile. From 1492, the Crown of Castile, under Charles I of Spain, also sponsored the first expedition of world circumnavigation in 1521. The enterprise was led by Portuguese navigator Ferdinand Magellan and completed by the Spanish Basque Juan Sebastián Elcano. The trips of exploration led to trade flourishing across the Atlantic Ocean between Spain and America and across the Pacific Ocean between Asia-Pacific and Mexico via the Philippines. Later, André de Urdaneta discovered the Northern Pacific Volta do Mar return voyage. The compass, a cross-staff or astrolabe, a method to correct for the altitude of Polaris, and rudimentary nautical charts were all the tools available to a navigator at the time of Christopher Columbus. In his notes on Ptolemy's geography, Johannes Werner of Nuremberg wrote in 1514 that the cross-staff was a very ancient instrument,
but was only beginning to be used on ships prior to 1577. No method of judging the ship's speed was mentioned that was more advanced than observing the size of the vessel's bow wave or the passage of sea foam of various floating objects. In 1577, a more advanced technique was mentioned, the chip log. In 1578, a patent was registered for a device that would judge the ship's speed by counting the revolutions of a wheel mounted below the ship's waterline. Accurate timekeeping is necessary for the determination of longitude. As early as 1530, precursors to modern techniques were being explored. However, the most accurate clocks available to these early navigators were water clocks and sand clocks, such as hourglass. Hourglasses were still in use by the Royal Navy of Britain until 1839 for the timing of watches. Continuous accumulation of navigational data, along with increased exploration and trade, led to increased production of volumes through the Middle Ages. Routiers were produced in France about 1500. The English refer to them as rutters. In 1584, Lucas Wagener published the Spiegel der Seefahrt, the Mariner's Mirror, which became the model for such publications for several generations of navigators. They were known as Wageners by most sailors. In 1537, Pedro Nunes published his Tratado da Esfera. In this book he included two original treatises about questions of navigation. For the first time the subject was approached using mathematical tools. This publication gave rise to a new scientific discipline, theoretical or scientific navigation. In 1545, Pedro de Medina published the influential Art de Navegar. The book was translated into French, Italian, Dutch and English. In 1569, Gerardus Mercator published for the first time a world map in such a cartographic projection that constant rum trajectories were plotted as straight lines. This Mercator projection would be widely used for nautical charts from the 18th century onward. In 1594, John Davis published an 80-page pamphlet called The Seaman's Secrets which, among other things, describes great circle sailing. It's said that the explorer Sebastian Cabot had used great circle methods in a crossing of the North Atlantic in 1495. Davis also gave the world a version of the backstaff, the Davis quadrant, which became one of the dominant instruments from the 17th century until the adoption of the sextant in the 19th century. In 1599, Edward Wright published Certain Errors in Navigation, which for the first time explained the mathematical basis of the Mercator projection, with calculated mathematical tables which made it possible to use in practice. The book made clear why only with this projection would a constant bearing correspond to a straight line on a chart. It also analyzed other sources of error, including the risk of parallax errors with some instruments, and faulty estimates of latitude and longitude on contemporary charts. In 1631, Pierre Vernier described his newly invented quadrant that was accurate to 1 minute of arc. In theory, this level of accuracy could give a line of position within a nautical mile of the navigator's actual position. In 1635, Henry Gellibrand published an account of yearly change in magnetic variation. In 1637, using a specially built astronomical sextant with a 5-foot radius, Richard Norwood measured the length of a nautical mile with chains. His definition of 2,040 yards is fairly close to the modern international system of units. SI definition of 2025.372 yards. Norwood is also credited with the discovery of magnetic dip 59 years earlier, in 1576, modern times. In 1714 the British Commissioners for the Discovery of Longitude at Sea came into prominence. This group, which existed until 1828, offered grants and rewards for the solution of navigational problems. Between 1737 and 1828, the commissioners disbursed some £101,000. The government of the United Kingdom also offered significant rewards for navigational accomplishments in this era, such as £20,000 for the discovery of the Northwest Passage and £5,000 for the navigator that could sail within a degree of latitude of the North Pole. A widespread manual in the 18th century was Navigatio Britannica by John Barrow, published in 1750 by March and Page and still being advertised in 1787. Isaac Newton invented a reflecting quadrant around 1699. He wrote a detailed description of the instrument for Edmund Halley, which was published in 1742. Due to this time lapse, credit for the invention has often been given instead to John Hadley and Thomas Godfrey. The octant eventually replaced earlier cross-staffs and Davis quadrants, and had the immediate effect of making latitude calculations much more accurate. A highly important breakthrough for the accurate determination of longitude came with the invention of the marine chronometer. The 1714 longitude prize offer for a method of determining longitude at sea was won by John Harrison, a Yorkshire carpenter. He submitted a project in 1730, and in 1735 completed a clock based on a pair of counter-oscillating weighted beams connected by springs whose motion was not influenced by gravity or the motion of a ship. His first two sea timepieces, H1 and H2, completed in 1741, used this system, but he realized that they had a fundamental sensitivity to centrifugal force, which meant that they could never be accurate enough at sea. Harrison solved the precision problems with his much smaller H4 chronometer design in 1761. H4 looked much like a large 5-inch, 12 centimeters, diameter pocket watch. In 1761, Harrison submitted H4 for the £20,000 longitude prize. His design used a fast-beating balance wheel controlled by a temperature-compensated spiral spring. These features remained in use until stable electronic oscillators allowed very accurate portable timepieces to be made at affordable cost. In 1767, the Board of Longitude published a description of his work in the Principles of Mr. Harrison's Timekeeper. In 1757, John Bird invented the first sextant. This replaced the Davis quadrant and the octant as the main instrument for navigation. The sextant was derived from the octant in order to provide for the lunar distance method. With the lunar distance method, mariners could determine the longitude accurately. Once chronometer production was established in the late 18th century, the use of the chronometer for accurate determination of longitude was a viable alternative. Chronometers replaced lunars in wide usage by the late 19th century. In 1891, radios, in the form of wireless telegraphs, began to appear on ships at sea. In 1899, the R.F. Matthews was the first ship to use wireless communication to request assistance at sea. Using radio for determining direction was investigated by Sir Oliver Lodge of England, André Blondel of France, De Forest, Picard, and Stone of the United States, and Bellini and Tosi of Italy. The Stone Radio and Telegraph Company installed an early prototype radio direction finder on the naval collier Lebanon in 1906. By 1904, time signals were being sent to ships to allow navigators to check their chronometers. The U.S. Navy Hydrographic Office was sending navigational warnings to ships at sea by 1907. Later developments included the placing of lighthouses and buoys close to shore to act as marine signposts identifying ambiguous features, highlighting hazards and pointing to safe channels for ships approaching some part of a coast. After a long sea voyage, In 1912, Niels Gustav Dahlen was awarded the Nobel Prize in Physics for his invention of automatic valves designed to be used in combination with gas accumulators in lighthouses. 1921 saw the installation of the first radio beacon. The first prototype shipborne radar system was installed on the USS Leary in April 1937. On November 18, 1940, Mr. Alfred L. Loomis made the initial suggestion for an electronic air navigation system, which was later developed into LORAN, Long-Range Navigation System, by the Radiation Laboratory of the Massachusetts Institute of Technology. And on November 1, 1942, the first LORAN system was placed in operation with 4 stations between the Chesapeake, Capes and Nova Scotia. In October 1957, the Soviet Union launched the world's first artificial satellite, Sputnik. Scientists at Johns Hopkins University's Applied Physics Laboratory took a series of measurements of Sputnik's Doppler shift, yielding the satellite's position and velocity. This team continued to monitor Sputnik and the next satellites into space, Sputnik 2 and Explorer I. In March 1958, the idea of working backwards, using known satellite orbits to determine an unknown position on the Earth's surface, began to be explored. This led to the Transit Satellite Navigation System. The first transit satellite was placed in polar orbit in 1960. The system, consisting of 7 satellites, was made operational in 1962. A navigator using readings from 3 satellites could expect accuracy of about 80 feet. On July 14, 1974, the first prototype Navstar GPS satellite was put into orbit, but its clocks failed shortly after launch. The navigational technology Satellite 2, redesigned with cesium clocks, started to go into orbit on June 23, 1977. By 1985, the first 11-satellite GPS Block I constellation was in orbit. Satellites of the similar Russian GLONASS system began to be put into orbit in 1982, and the system is expected to have a complete 24-satellite constellation in place by 2010. The European Space Agency expects to have its Galileo with 30 satellites in place by 2011-12 as well. Integrated bridge systems. Electronic integrated bridge concepts are driving future navigation system planning. Integrated systems take inputs from various ship sensors, electronically display positioning information, and provide control signals required to maintain a vessel on a preset course. The navigator becomes a system manager, choosing system presets, interpreting system output, and monitoring vessel response. See also: air navigation, Austronesian navigation, celestial navigation, Galileo positioning system, geodetic system. Great Circle Distance explains how to find that quantity if one knows the 2 latitudes and longitude. History of longitude, Marjun, Shen Kuo. List of explorers. Maritime and History of the United States. Marshall Islands Stigchart. Navigation, Polynesian navigation, South-pointing chariot. Franz Xaver, Baron von Zach, a scientific editor and astronomer, first located many places geographically. Rumbly, Grid. Notes. Bowditch, Nathaniel. 2002. The American Practical Navigator. Bethesda, M.D. National Imagery and Mapping Agency. ISBN 0-939837-544-4. Cutler, Thomas J. December 2003. Dutton's Nautical Navigation. 15th ed. Annapolis. M.D. Naval Institute Press. ISBN 978-1-55750-248-3. Department of the Air Force. March 2001. Air Navigation. PDF. Department of the Air Force.
retrieved 17 April 2007. Great Britain Ministry of Defence. Navy. 1995. Admiralty Manual of Seamanship. The Stationery Office. ISBN 0-11-772696-6. Maloney, Albert S. December 2003. Chapman Piloting and Seamanship. 64th ed. New York, NY. Hearst Communications Inc. ISBN 1-58816-089-0. National Imagery and Mapping Agency. 2001. Publication 1310. Radar Navigation and Maneuvering Board Manual. PDF. 7th ed. Bethesda. MD. U.S. Government Printing Office. Chisholm. Hugh. ed. 1911. Navigation. Encyclopaedia Britannica. 19. 11th ed. Retrieved 17 April 2007. Chisholm. Hugh. ed. 1911. Pythias. Encyclopaedia Britannica. 22. 11th ed. Retrieved 17 April 2007. Billich. Tomislav. March 2009. The Myth of Alpheus and Arethusa and Open Sea Voyages on the Mediterranean Stellar Navigation in Antiquity. International Journal of Nautical Archaeology. 38. 1. 116-132. DOI. 10.1111, J. 1095-9270.2008.00189. X. Bloomberg, Mary. Goran Henriksen. 1997. Evidence for the Minoan Origins of Stellar Navigation in the Aegean. Actes de la Conférence Annuelle de la SEAC. Gdansk. pp. 69-81. Taylor, E. G. R. 1971. Link. Eds. The Haven Finding Art. A History of Navigation from Odysseus to Captain Cook. New York. American Elsevier Publishing Company, Inc. Homer. Link. Eds. The Odyssey. Book v.